Agenda for today is I'm going to answer the questions which you have asked in the Google form, and Simran will be answering the questions in the chat window. So at time if I have my YouTube screen open with me, so if at any time I feel I can pick some question from there, I'll take it up and discuss it. I have received around 71 questions from your side, but then yes, certain questions are similar. So based on the similarity of the questions, I have sort of clustered them. So you already see some kind of community detection going on here. I'll discuss those similar questions under one bucket, and if at the end of the session you feel like your question is left out, you can again write it in the chat window and we'll address that. So just give me a second. I'll share my screen and get started. I don't have slides, but most of the things which I want to show you, I can show those to you through a Google screen. Just a second. Yeah. Just give me 1 second. I want to. Okay. All right. So I'm addressing the first question here, which is regarding the data sets. Many of you have asked regarding the data sets, and I would say the best way to look up for anything when you are confused is to simply Google it. I'm going to show you a whole lot of network data sets here, and when we see these data sets, while looking at the data sets, we'll also look at some applications of these. So let me simply type here network data set. So if you simply do a Google search with this, you'll see a whole lot of data sets here. So let me show you some of these. So this one data set collection is from Stanford University. It is the one which is used the most by people, but I would say that several data sets which are here are actually quite old. They keep adding new data sets as well. Whenever you are doing a piece of research or you are doing some network analysis, it makes sense to use more recent data sets. All right. So as you see the first kind of networks which you see over here, these are social networks. And when you see a Facebook network here, it's not the entire Facebook network. It's an induced subgraph on few users of Facebook. So as you can see that there are 4,000 nodes in this network. So there are several other data sets from several other websites. So one point which I want to make here is, although the course which we are teaching to you is social networks, but the principles which you learn in this course, you can actually apply them to almost every kind of network. So you need not remain limited to social networks after this course. So if you move further, you'll actually see various different kinds of networks over here. So I'll talk about this one later. So you see communication networks here, you see citation networks over here, right? So the point is, whatever we are teaching you in social networks, there are certain properties associated with networks. I think you have seen a few of them. As an example, there's always this giant component in the network. Network has lot of triads, networks have communities. So you don't just see them in social networks, you see them in a lot of other networks as well. So the same principles apply to your communication networks, citation networks. And whenever we talk about these networks, so let's talk about the citation networks, it always helps to think about what the study of these kind of networks will yield us at the end. So to show you that, so definitely you can import these data sets in a Jupyter notebook and you can work with them. But let me show you a very good piece of research which has been done by Nature, which is one of the world's topmost journals on these kind of citation networks. So I'm giving you 5 minutes here. So you can just put the current YouTube window on mute and just try to search this on Google. So you can search this video just by its title. So I recommend each of you, this is the only video watching which we are going to do during this live session. For the remaining session, I'll be taking your doubts. So can you just search this title in a YouTube window and watch this video? So although this network here looks like a galaxy, but this network here is a network of publications, and you can see what all interesting results they have come up with this network. They have seen how knowledge emerges in the world with the help of research papers, and they have done it from a networks aspect. So I'll give you 5 minutes here, and I'll again start speaking after 5 minutes. Okay, all right. I hope that you enjoyed the video. So the point in showing this video was you can see what kind of research can be done on a citation network like that. And let me show you a few more networks here. So someone even asked a question about these kind of web graphs. So when we talk about these web graphs, here is the question. So what is a web graph? Essentially, all the web pages which you have on internet, they are the nodes. And if one page has a hyperlink to another web page, you will see an edge between them. Now the question is of what use can such a network be? Do you have any idea what one can do with this kind of a network? It doesn't seem to be very useful, right? So back in the year 1990s, to Stanford students, they actually dropped their PhDs and they worked on this network. All of you would know about search engines. And back in 1990s, people, they were working towards building these basic search engines. So there are these web pages outside which have a lot of information. And let's say I want an information on a certain topic. So a search engine is kind of an algorithm, or you can say a kind of a software to which I'll tell the topic which I'm looking for, and it will figure out the best pages from internet regarding that particular topic. So back then in 1990s, internet was very small. There were not a whole lot of pages. So one could even do this manually. But people realized at that time that with time, this internet network, it is going to be huge. So how will you search for relevant pages during those times? So one idea which comes first to the mind is utilizing the content of these pages, right? If I'm searching for apple or let's say fruit, so it makes sense to search all those pages which mention apple a lot of times or which mention the word fruit a lot of times or their respective synonyms. So initial search engines were mostly based on this kind of content, but these two researchers, they actually utilize this web graph and came up with an algorithm which is called Google PageRank, which changed the history of search engines. So even today, you might realize that most of us, we use Google search for searching our queries. Try to use a different search engine and you'll note the difference really quickly. So the question is, how do they exactly utilize this web graph to figure out which are the best pages, and why does this approach even gives you the best web pages? So that will be discussed during coming up weeks in the course. All right. Then there are certain datasets regarding product co-purchasing networks. Again, a question here of what use can such a network be? So such kind of networks, you can use them for recommending products to people. So if I know that these two products, these are purchased really frequently, so if you purchase one of those products, I can recommend the other one to you. So this is like putting recommendation systems in a very naive way, in a very easy to understand way, but there are a whole lot of advanced algorithms as to how to recommend products to people. And again, networks play an important role there. Then there are more of such networks. If you see here, signed networks, again, we have devoted like 1 week of the course to the study of signed networks. So why should I only display friendships in a network? Can I not display animosity? Can't I see how people hate each other? And can that tell me something about the networks? And as you'll see during the course, we'll talk about that. And people have used such kind of studies to see if a world war happens, or which countries will align with which other countries. So let me actually show you a fairly recent piece of research here. This is by a few IIT students, and they have tried to predict which countries will fight together in World War III, and how will the clusters be. They have done it with the concept of signed networks. So don't worry if you don't know what they are. We'll discuss that during the course. So if I go down, they utilize these kind of relationships between the countries, what kind of exports and imports these countries are involved in, their diplomatic relationships, and their peace treaties, etc., to actually figure out with time which countries will fight with each other and which against each other. So this is the If I go down, yeah, this is the result of this study. So they have seen that probably we'll have two coalitions and they have played some countries with each other, some without each other. So we are not going to discuss more on political grounds here, but the idea is that you can use a social network to predict all these kind of fancy things. And many a times these predictions actually come true. So if I can just go back and show you a few more networks here. These are some temporal networks where along with edges, you also have the time at which those edges arrived. Gautam, you can go back, look at that paper and see, do we have India in the list? I'm not very sure. Because that's like a small graph, so probably they have shown the most important countries there. This is another data set which is fairly recent, not but still like 10 years old, but relatively recent from other data sets. Here they give you a whole lot of Twitter data. So this was the time when the Higgs boson particle was discovered. It gives you a web graph on Twitter and it shows you how this information regarding Higgs boson particle, it was spreading on Twitter. So you can use these kind of data sets to study how information diffuses in a social network. That's again one of the chapters in our course, which is towards the last week, which is the 12th week. All right. So we have all these kind of data sets. Let me show you a few more data sets here. So I have just Googled it, right? So you can go and explore all of these different data sets here. So one thing which you need to take care of, once you want to work with these data sets, different websites, they'll give you these data sets in different formats. So some of these websites, they will give you edge list as a CSV file, and then some of these will give you graphs as a GML in a GML format. So you should know the relevant packages. I think they have been discussed in the course, and it's fairly easy to import all these data sets and work with them. But yes, one thing is some of these data sets, they are like huge. They are very, very big, and you cannot crunch them with just your laptop. You might need a high-end machine. Or better even, what you can do is you can look at some graph sampling techniques where you do not load the entire network, but a subpart of the network, which represents the network well, and then you can do your study on that part. All right. There is one more data set which I wanted to show to you apart from all this, which is again very famous. So it's called the Connect project. If you go here and if you browse networks, you have around 1300 networks over here. Right? So again, you can study all of these, and there are different kind of networks as you see. So B here stands that the network is bipartite. That is, it has sort of two kinds of nodes, right? And U is for undirected, D is for directed. If you see plus here, this corresponds to weight. So you can always go to it and learn more about it. All right. I'll also show you one more interesting resource. Yeah. This will be useful to you if you are looking for some data set which is from the real world, not a data set which was like crunched by people and they put it on the website some years back. So if you are looking for some real world data set, here is something which you can use. So this project is from Indiana University. I think it came in around the year 2013 or 14. So if you go to this and click on tools here, so there are a whole lot of tools here which you can go and check. So the one which I personally like is the networks over here. So you can actually crunch networks from what is happening just today on Twitter or what happened yesterday on Twitter. Just give me a time. It's taking some time to load. All right. So if you see here, let me write a hashtag here. So let's say I'm searching for Omicron. So it will fetch you some tweets, but not the content of the tweets. It will give you entire retweet network. It will tell you in the past few days or even in the past few months who tweeted about this hashtag to which other person. So let's set some dates here. So I'm just taking it from 6 to 7 Feb, and let me generate this network here. Since the data set is huge, it takes some time to come up. Okay, meanwhile this comes, uh, there is this again very interesting project which has been done in 2020. So somebody talked about, I don't remember the name of the person, I'm sorry. So yeah, so someone talked about genome sequencing and how social networks can be useful there. So in that context, there is this problem which is called protein folding problem. So if you look at these data sets, there are a whole lot of protein-protein interaction kind of networks, and they show you how proteins interact in the body. But there is this another problem which says that everything which is there in the body and this world exists because of proteins. So it's all about so if you look at a protein, it is nothing but it's a sequence of amino acids, and it's all about the connections between these amino acids. So these amino acids, they fold in different ways. So if I can just get rid of this, I can show you. Just a second, so if I could close it. Yes. So this figure here shows it. So this is a sequence of amino acids, and these amino acids, they actually fold into proteins, and when they fold, they make three-dimensional complex structures. And from hundreds of years, people, they have been trying to predict that if you are given a sequence of amino acids, can you predict what kind of a three-dimensional protein structure it will result into? And it's a very important problem, because how these proteins unfold, they decide a lot of things. They also decide whether someone will develop cancer over a period of time or not. They decide on certain diseases. So if you could predict well in advance how it will fold, you can actually change a lot of things. And people, they had been trying to do it with all sort of computations and visualizations. But again, it was only in the year 2020 that there was this project which came up, which is called AlphaFold. You can look it up on the internet. It's like one of the biggest discoveries of the year 2020. So there they have used the concept of social networks along with deep learning to actually predict this thing, and they are doing it really well. So that is one of the most advanced discoveries in social networks in a few years of time. Rather, if you are more interested to learn about this intersection of graphs with machine learning, there is this course by Stanford University. It came in the year 2021, just like in the last year. So if you are looking forward to advance your knowledge further and do a whole lot of things with social networks, this is something which you can. So after doing this current course on social networks, once you learn the basics of networks, and if you are well versed in machine learning, you can look up in this course. Okay, let me, my net has been turned on. Okay, it's taking some time here. Let me just try once more. Okay, all right. Okay, so if you wait for some time here, it will give you a graph. And the idea is once you have this graph, you can download it in CSV format or GML format. You can play around with it. You can see who was talking about Omicron. And apart from the retweet and quotes network, you can also look at mention and reply network. You can look at co-occurrence network. This alongside Omicron, which other hashtags were people talking about? So which hashtags are related to the hashtag Omicron? So as of now, I'll close it. I think it's a lot of information I'm giving you, but you can always watch this live session back. You can try these things out and you can write to me or you can write on the discussion forum of the course if you face any problem here. All right. So let me just close this window. Yeah. So apart from these things, apart from these high-end projects, so someone asked me the question about other practical projects which you can do in this course. Let me actually show you some projects. So one of the key ideas in social networks is about to study a friendship network. So here is a little study which we have done. It's just a small project which has been done in an institute. Trust me, it's difficult to collect data like this. So we collected this data regarding the friendships between the students in an institute of the same batch. And we tried to look at the network and we try to see whether it has the same properties as a real world networks, just to validate the research with the old research works. And we could see that yes, there were communities in the network. And I'm going to talk about communities a bit more in the coming up session, because some of you had some interesting questions regarding community detection and communities in social networks. Well, so we saw in this network that these communities, they were many of these, they were based on the geographical location of the participants. Some of them were based on the gender of the participants, so on and so forth. So there are more kinds of things which you can do with it. So you can actually try to correlate the positions of nodes in this network with the marks of the students. So what do you think is someone who is at the center of the network? You will study more about centrality measures in the coming up videos, right? So someone who is in the center of the network, do those kind of students get better grades than other students, so on and so forth. So if I could just drag down and show you a few more things here. So in addition to the friendship data, we also collected this kind of data between the students. The idea was to see the academic relations between the students. So if you have got a query in a particular course, which person are you going to approach? And this is the kind of data set which we saw, where you will see a whole lot of hubs and star networks. And most of these star networks are the students which get good grades. And then there are certain students which get good grades, but no one approached them. So again, it's a sociological question to ask why these kinds of things happen. So we have again seen a lot of interesting things in these kind of networks. One thing was there were certain students who dropped from the third semester of their course to the fifth semester. And if you look at those students, they were mostly those who do not have, who didn't have friends, enough friends, right? So which again brings you to a conclusion that if you have less friends, then you're more likely to drop out. And yeah. Another kind of so if I close it and close it, yeah. Another kind of practical work which can be done. So the idea is you can apply the science of social network to any kind of data where you can see some kinds of nodes and edges, where you can see relationships between entities. Now these entities, they can be people, they can be companies, they can be banks, they can be living organisms. So if you recall about food chain, which we used to study in like in fourth and fifth standard. So that's also a network, right? Not a social network, but it's still a network. And today people study those networks in the form of ecological networks. So if you look at the big food chain consisting of all the organisms or a whole lot of organisms in the world, This is another kind of work which one can do. It is about studying the corporate network of a country. It is more like a bipartite network. So again, you should read a bit of discrete maths to understand what a bipartite network is. But I'll just rephrase here a bit. So bipartite network is one where you have two different kinds of nodes. So if you look at this corporate network over here, you have certain nodes which are people. So these are the CEOs of companies, and you have another nodes which are the companies itself. So if one person sits on the board of a particular company, you will put an edge between that person and that company. So you see here, you won't see edges between two persons. You won't see edges between two companies. It would always be between a person and a company. So once you have this kind of bipartite network, you can study it. So the idea is you can get rid of this bipartiteness. You can convert this network in a unipartite network. How? So I can sort of ignore all the companies and I can make a network between the CEOs, and I'll connect two CEOs if they sit on the board of the same company. Then it's highly likely that they know each other if they're sitting on the board of the same company. You can also make the edges weighted here. So an edge will be more thick if two people, they are sitting on the board of several companies together. And then you can study such a network. You can figure out which are the most important companies in a nation, which are the most important directors in a nation, and it can help you answer few queries related to recession and other things. So which company is the one which will be most protected during the time of recession, all those things, right? I've just given you a few ideas here regarding what all kind of networks can be studied using this course. So let me now go back to a few implementation related problems. So I see that some of you have queries regarding the version of NetworkX which we are using. So these lectures, they were recorded like a few years back when we had an older version of NetworkX. And here is the solution to your problem. So I have seen on discussion forum that most of the time, so one idea is you can keep using the current most updated version of NetworkX. If you have a query, you can post it on discussion forum, you can search it on Google, and you can resolve that. Another idea is you can just download an older version of NetworkX and you can work with it, right? So if you see here, here are two commands which you can use to go back to the older version of NetworkX, and maybe matplotlib also if you are facing some problem with that package, and you can use these older versions, right? And then the codes which you have in the video will work well. There is an additional thing which I wanted to show you. I'll stop my video for a while and I'll just open this Jupyter notebook. Yeah. So we have a lot of packages to study about these networks. So Jeffy is something which has been introduced to you. Jeffy is a graphical user interface which is easy on mind, and you can use them for studying smaller networks. But most of the times when you take this course for some kind of research and you want to build up things with this, you work with networks which are much larger in size. What helps in those cases are the Python packages. NetworkX is the one package which we have introduced to you in the course. So the part of this live session today, I'm going to introduce you to one more package, which is igraph. And you can, igraph is has developed a whole lot in the recent years. So if you are looking for faster codes and more functions, you can actually switch to igraph. And trust me, in Python, switching from one library to another is fairly easy. I understand that switching from one language to another might require some effort. So if you're working in R and suddenly you are asked to switch in Python, it might take an effort, but working with libraries in Python, it's really easy. So what I'm going to show you, I'm going to now show you a quick code in using this another library, which is igraph. I'm going to show you some starters code and you can explore it further if you are interested. So just like NetworkX, we have this another package which is called igraph. Right. So here I have just imported this package here. I hope that my screen is visible. Let me see, I can just zoom in slightly. All right. So right now I'm looking for creating a very simple graph here with no nodes and no edges. So I have this command which is called graph. And this creates an empty graph for me. So you can see some of the properties of this graph here. So if I print this graph here, you'll see that it's an undirected graph. It has 0 nodes, it has 0 edges. Right, so let's try to add a few nodes and few edges to this graph. So these functions which you are seeing here, you can always go on Google. You can look up the documentation of igraph. You can also look up at certain blogs and you'll find all these functions there as well. So as of now, I'm adding 5 vertices to this graph. So if I again print this graph here, you can see that now I have 5 vertices and no nodes here in this graph. It is quite similar to NetworkX, just that the package is different and the name of the functions might slightly vary. And then let's say I want to give each of these vertices some name or some label. So what I'm going to do, so g.vs is a vertex sequence object. So if I print this for you, you can see that it's a vertex sequence object. So I'll just print it as a list here and show it to you. Right. So this is your vertex sequence object. It just shows you that you have 5 vertices in the graph and they have been indexed from 0 to 4 in this network over here. All right. So next I'm going to add some attribute to this vertices. So let's say I'm adding this attribute, which is called the first name. This is the command. So to this vertex sequence, with each vertex, I'm going to associate this attribute, which is f name. Since I have 5 vertices, I'm going to pass it a list, which is having 5 names. So let me randomly write some 5 names here. All right. Okay. Let me again print this graph. And you see now, you see that here I have an attribute, which is a vertex attribute, which is f name, which we just created now. All right. So once we have these attributes, let's say you want to retrieve these attributes, that's also fairly simple. So I just write a f name here and you'll see the first names of all these vertices. If you want to see the f name of a particular vertex, say the 0th vertex, you can just write a 0 here and put f name here. It will show you the first name of the 0th vertex. Okay, if you want to retrieve a particular vertex based on the attribute, what you can do is g.vs. So I'm looking for that particular vertex, let's say whose f name is Nihal. Right? So it will give you a vertex sequence. So basically it will return you all the vertices who have the first name as Nihal. So as of now, we have only one vertex with this name. So you can, so this vertex sequence, it's actually an iterator over here. So you can iterate over it and see which all vertices are there in this. So how you can do it is, let me just store it in a variable. Let me name the variable as v. And what you can do is, for each in v, this v is an iterator which is having all the vertices which have first name as Nihal, and I can print v dot index of this particular vertex. Oh, so sorry, I should write each here, right? So it shows me the index of this particular vertex is 2. So there are a whole lot of functions like this which you can check. We also have a function to add edges, similar to add vertices. To this function, so I'm sort of assuming here that you are well versed with the basic Python. To this function, I'm going to pass a list of tuples. So this is a list, and I'm going to pass it a tuples which have all these edges which I want to put in this graph. So this is just some additional information which I'm giving you. You can definitely stick with NetworkX, but if you are thinking to do something more with networks and you are looking for packages which are faster, you can use this. Okay. So okay, I got an error here. Okay. okay, I do not have, so I have 5 vertices, right? Not, so from the indices 0 to 4. I wrote here 3 to 5. That's what it was giving me an error. So I added these edges here. And if you want to see this network, so here you don't need any matplotlib. IG has its own function, which is called float. And you can pass this graph over here and it will show you this graph here. Right. So it's just that the way which we have added vertices are from 0 to 1, 1 to 2, 2 to 3, 3 to 4. That's why it appears like a chain here. So let me add 2 to 3 as well. If I run it again, then you can see that I have few more edges added here. Now I have multiple edges, right? I have added some of these edges 2 times. So you see all those edges 2 times here. And then there are more parameters which you can pass in here to make this plot look better. So as an example, let me show you one parameter which is called edge underscore curve. You can choose to curve or not curve these edges. So look at this. Right? So if I use edge underscore curved, each of these edges is slightly curved. Right? And the point is, so I still have 2 edges over here, but when I use this edge underscore curve, these edges are sort of overlapping here. So now you just see them as one edge. All right. So I just wanted to show you the existence of one more package like this. You can explore it further and you can talk to us if you want to work more using this package. All right. Let me move on to a few final things. So Rishabh has this had this question about finding communities in a graph. So at this point, I'll also like to highlight the difference between components and communities. So sometimes there is a confusion regarding these two terms. They are slightly different. So when you talk about component, it's like in a graph, you have several graphs, right? So let's say I have 2 graphs and I see them as one graph. So I have 2 components there, 2 disconnected components there. Disconnected means they don't have an edge with each other. And we have seen that it is generally not probable in a network that it will happen like this. So there's a video in the first week of the course which actually shows you it is very less probable that you have 50 students this side, 50 students this side, and you won't have any connection between those. So if there is no connection between this 50 on the left and the 50 on the right, it actually means that they are 2 components. So components do not have any edge with each other. When you talk about communities, you can have connections between the communities. Let me actually show you how a typical community structure look like. So if you see this figure here, just go down, let's expand it. Yeah. So this is a figure which shows you communities. Now please note that these are not components. This entire thing is one graph, one connected graph. So you don't have any components here, but still you can see 3 communities here, right? 3 communities in what sense? So if you look at these, Aditi, you want to say something? Is it possible for you to write it in the YouTube window? Let me see a few chat here. Is my screen visible? Can someone tell me? I hope my screen.
Yes.
All right, all right.
Can I ask like by speaking only?
Yes, tell me.
Ma'am, we can see the communities here, but if the communities are not visible, then how can we arrange the graph such that we are able to see the communities?
Yes, yeah. So that is a question which we should answer here, right? This is a very small network and it is shown to you in such a way that you can see the communities here. But that won't happen if I give you a graph on a million nodes. You can't put it on a sheet of paper and you can't just visualize it with your eye. Where are the communities? So there is the idea that we should have certain algorithms to which we can give the adjacency matrix of a graph, or I could just tell this algorithm that these are the edges in my graph. And now you tell me which are the communities and how one should design these algorithms. there are like thousands of papers written on this topic, and people are still writing. So there are certain very base ideas which you can use. So one idea is regarding betweenness. I'm not sure whether that those much of weeks have been covered in the course as of now or not. So betweenness says, so you see this edge in this network, it's sort of responsible for connecting two communities, right? So the idea is, with each edge we associate a score which is called betweenness. Betweenness is nothing but you take every pair of nodes in this graph, right? So take this node here and this node here, then this node here, this node here. So you'll have and choose two pairs, right? So for each of the pairs, you figure out the shortest distance between those pairs, and you see on those shortest pairs how many times do you see these edge in that shortest path. So if you will see these kind of edges which are running from one community to another, you will see them in a lot of shortest paths, right? So if you want to go from this node to this node, this one or this one, you don't need this edge here. But if you want to go from any node from this community to this one or this one, you'll have to pass through this edge, right? It will be formally covered in the course. But the idea is, if I want to go from one part of the graph to another, which are the edges which you will see a whole lot? You figure out which are those edges and you start dropping them. Once you drop them, soon this network will disconnect. You see, so in this network, the edge betweenness of these edges will be very high. So once you drop this edge, so there are essentially four edges here, this one, this one, this one, and this one. So if you drop these four edges, this network will disconnect in three components. And then you can say that these are my communities.
Ma'am, you are assigning betweenness by doing random walks, right? You will be walking randomly on the graph.
So you can, random walk is another approach. You can also employ that. Just give me a second. So I'll share my screen through my iPad and I'll give you an idea of how exactly to do this. Okay. All right. So I'm taking a very simple graph here. Let's say this is a graph I have. I think my iPad screen will come up in a while. Okay. Stop sharing from here. Just a second. Yeah. So let's say this is the graph here, right? And I'm interested in figuring out the communities in this graph. So how exactly do we do that? And let's say I am not visualizing this graph. I just have the adjacency matrix of this graph. So how do I know that there are these communities without actually visualizing this graph? So what you do is, with each of the edges here, you calculate something which is called betweenness. It's a proper theoretical concept. So here you don't do any random walk. What you do is, so let me name the edges as 1, 2, 3, 4, 5, 6, right? So take this node pair 1 to 2, right? And see, okay, how many shortest paths are there between 1 to 2? There is only one shortest path, right? And let's say I'm computing the betweenness of this edge here, 3 to 4. And you see, does edge 3 to 4 lie on the shortest path? No, it doesn't. So I put a 0 here. Again, you see from 1 to 3, it doesn't lie there. So a 0 here. 2 to 3, it doesn't lie here. So a 0 here. Now the idea is, when you take these pairs 1 to 4, so you'll have to pass through 3 to 4. So I'm not taking a random walk here. What I'm looking at is the shortest paths between all pair of nodes. So between 1 to 4, how many shortest paths are there? So this is the shortest path, right? Its length is 2. I think this is the only shortest path we have, right? And this edge 3 to 4, it lies on that shortest path. You cannot go from 1 to 4 without passing through this edge. So I place a 1 here. Then go further. If I want to go from 1 to 5, again you'll have to pass through this edge. So I put one more here. So if you have to go from 1 to 6, again one here. You want to go from 2 to 4, one more here, right? So this is how you formally define it. So let me rather put it as for every node pair, you look at, so let's say the node pair is UV, you look at the total number of shortest paths between U and V. So let me represent it as delta UV. This is the total number of shortest paths. You can have more than one shortest path between two nodes, right? And in the numerator, you keep the number of shortest paths which have this particular edge for which you are computing the betweenness. So let's say I'm computing it for the edge E, right? So the number of shortest paths delta UV on which you have this edge E, on which you have E. Uh, so just try to understand the intuition of it. So the idea is these edges which are running between two communities, they have very high value of betweenness because they lie on a whole lot of shortest paths. Right? So you compute this betweenness for each of the edges and you drop the edge which have highest value of betweenness. Right? So this is just one approach. You can have a whole lot of approach. So there are two kinds of approach. One they call it divisive. So this one is a divisive approach. You try to break the network into components. You try to remove some edges and then you try to break it in components. There is another approach which is called agglomerative. So that can be based on something like a random walk. So the idea is maybe, okay, I'll start from any one node in the network and then I look at some of its neighbors and maybe those neighbors to which it is strongly connected. How do I know it is strongly connected with other neighbors? So let's say I have something like this. So you can start from here and then I will pick up one more vertex which is likely to be in the same community. Which vertex is likely to be in the same community? Not this one because it has a whole lot of other friends, right? There is no good neighborhood overlap between these. But if I pick up this node, I have a good amount of neighborhood overlap. I have two common friends with this node. So it is likely that it is in the same community. So you can figure out more edges and you can just create communities with time by adding more and more nodes in this. So I'm just giving you an idea of how you can get started with it. So there are a whole lot of approaches to do it. Rather, okay.
Ma'am,
Yes.
so we are removing the edges, and when do we know that we have to stop at this point? Like we cannot see the graph now.
That's a good question. So you see, if you have studied a bit of machine learning, it's like when you do this hierarchical clustering, how do you know where exactly to stop, right? So when you do these methods, you get something which is called a dendrogram. You can look at the dendrogram and then you can decide where you want to break. And I'm sure there might be other techniques which you can use. So one idea which you can use, it's called modularity. So modularity actually tells you the communities which you have predicted in the network, how good those communities are, right? So let's say this is the network which I have, which you see on my screen. So one idea is I could have predicted the communities as you see in this graph, but I could give you a different result. I could say, okay, all right, these 4 nodes and these 5 nodes, they are in one community and this is another community. So I can give you 3 communities. I can also give you 2 communities. How do I know which result is better? Right? Same idea we can apply to betweenness. So when I'm breaking the graph based on these communities, how do I know when I should stop? So you stop when the value of this measure, which is called modularity, is highest, right? So if I'll give you a very basic idea of what modularity is. So if I superimpose a random graph on this graph, so this graph has 4 plus 5, 9 plus 5, 14 nodes. So I can take a random graph on 14 nodes, which has the same number of edges as this graph. And if I superimpose that random graph on this graph, how well do you think the communities are? Right? If the overlap is a whole lot, then probably the communities which I have predicted are not that good. Right? So don't worry about it. We'll also discuss it as the course proceeds. I can also take it up in another live session.
Thank you.
Okay. So I just wanted to show you a few more things. If you want to know more about various community detection algorithms, you can actually refer back to this paper dated January 2010. This is a paper written by Santo Fortunato, who works a whole lot in community detection. It's more like a literature review kind of a paper, and it gives you all the approaches nicely divided which are used for community detection. So you can take a look at it and we can argue more on this. So as of now, you can just make note of all these websites and papers which I am telling you. There was another very nice question by Aditi and Prasanna. So I'll answer both of these questions quickly, and maybe after that we can sign off from this live session. So one question was, when we are creating this friendship network in our course, so are we sort of saying that the friendships are random and they can occur between any two people? No, right? That's not true. So if we go by the very basic network model, which is random network, then yes, we are doing that. But yes, we know that that's not the best way to do it, because as you would have seen that most of the real networks, they have this decreasing power law degree distribution. So that's why we have more kind of models out there, right? So that's not true. We don't always use just random links. There's been a whole lot of research to actually create networks which look exactly like real world networks. And in that sense, there is a question, how do I create a network, a synthetic network which has communities in it, right? So I'm sorry. So for that also, there is this very nice resource. It's again from the Santo Fortunato's web page. So you can take a look at it. So just make a note of it and look at it. So you can read up this paper. It actually helps you create synthetic networks which are more real world like, in the sense that they have this power law degree distribution and they also have communities in it. And he has also given you the code here. So there are 5 different packages here to create different kind of communities. Okay, so with that, I'll stop. If you have more queries, feel free to drop them in the discussion forum. And if there is something which needs a lot of discussion, I'll take it up in the next slide.
Excuse me, ma'am.
Yes.
Ma'am, the NetworkX Erdos-Renyi graph back part, that isn't that that is not a random graph, right? The one we use, or is that making
That's a random
communities?
graph. Erdos-Renyi model
Okay.
creates a random graph. So you have 3, I think, 3 functions. One is Erdos-Renyi. This creates a random graph. Other is Bot-Strogatz, that creates a small world graph. And then the one is Barabasi-Albert, which comes closest to a real world network, in the sense that it gives you a power law degree distribution.
Okay, ma'am. Yeah.
All right, let's stop here. So feel free to drop in your queries to the discussion forum. Right. Okay.